These are the video notes for Objective 3C, Writing Polynomial Equations. In this portion of the video notes, we're going to focus on writing equations algebraically given the zeros. So for our first example, we're focusing only on rational zeros, which means fractions or whole numbers or integers. We are going to write the equation of a polynomial with zeros 1, -2, and 3, and assume a leading coefficient a equals 1. Well, if you have the zeros, x equals 1, x equals -2, and x equals 3, the next step is to turn these into factors. X minus 1, x plus 2, and x minus 3. Finally, we want to turn this into a standard form polynomial by multiplying everything together. And the part where it said a leading coefficient of 1, it just means that the number out in front should remain 1. So we'll just x times x. Now be careful, when you're multiplying polynomials, you can only do them 2 at a time. So I have to leave the x minus 3 out of the problem until I'm done simplifying the first step. Now I'm ready to multiply this trinomial to the binomial. And that is how you write a polynomial equation. Let's take a look at example 2, where the zeros are still rational, but now we have multiplicity. So we've got zeros, x equals -1 with multiplicity of 2, and a 0 at x equals 1/2. First, we're going to turn these zeros into factors. And we're going to save the such that portion for just a little bit later. So turning these into zeros, we get x plus 1. Multiplicity of 2 means that we need to square it. And then to write x equals 1/2 as a 0, we need to write 2x minus 1. And then don't forget to set it equal to f of x, so that it's a polynomial equation or polynomial function. From here, we still need to multiply this out. The difference is we're not assuming a is 1, and we need to put an a in front. And then we take our extra given information, and that extra given information was that f of 1 equals 6. And so using this information, we know that x is 1 and y is 6. And we can plug this in to find our missing front coefficient, a. From here, 1 plus 1 is 2 squared. That's 1. A in front, 6. So we've got 6 equals 4a, which gives us a solution that a equals 3/2. Now that we know our front coefficient, we leave that out in front, a equals 3/2, and we go ahead and multiply out our factors. So we're going to take f of x equals 2/3, and I'm going to start by multiplying x plus 1 times x plus 1, and then I'm going to multiply it by 2x minus 1. X times x. And that simplifies to be x squared plus 2x plus 1 times 2x minus 1. And this whole time, really, we should be bringing down the 2/3 with us, but we're not using it until the very end. Final step is to multiply here all the way through. That's going to cancel, and so we're left with 2/3 times 2x cubed plus 3x squared minus 1. We can distribute out the 2/3, or we can leave our answer like this. If you distribute it out, it becomes 4/3 x cubed plus 2x squared minus 2/3. And there's our second polynomial equation. For the next two examples, when we look at irrational and imaginary zeros, we have to pay attention to something called a conjugate. So a conjugate is a form of an inverse that allows us to rationalize irrational and imaginary solutions. In this first one, we know that the zeros are x equals 2 plus rad 3, and that the other zero is x equals 2. Well, our goal is to write a polynomial with rational real coefficients. And if we use this zero by itself, we're not going to get rational real coefficients. We're going to keep irrational numbers. This is where the conjugate comes into play. For every 2 plus the square root of 3, there has to be a balancing 2 minus the square root of 3. When we write these as zeros, it's a little bit tricky because we have x minus 2 plus rad 3 and x minus 2 minus rad 3, as well as our simple x minus 2. Distributing, we get x minus 2 minus rad 3 and x minus 2 plus rad 3 times the x minus 2. Notice we still have conjugates. There's a minus rad 3 paired with a plus rad 3. For multiplication, you always want to multiply the conjugates together first because the conjugates will eliminate all of the irrational numbers. For this 3 by 3, I'm going to use the box method just to keep my scratch work organized. We're going to create a 3 by 3 box for the x negative 2 negative rad 3 and the x negative 2 positive rad 3. Filling in each square, we get x squared minus 2x times rad 3x. In the next row, negative 2x, positive 4, and negative 2 rad 3. Remember, integer times an irrational is an irrational. Here we have negative x rad 3, positive 2 rad 3, and negative rad 3 times rad 3 is negative rad 9, but rad 9 is 3. If we did this correctly, all of the irrational terms should eliminate each other. Positive rad 3x and negative rad 3x, positive 2 rad 3 and negative 2 rad 3, and then we just need to combine like terms. This leaves me with x squared minus 4x plus 1, a really simple trinomial. Unfortunately, I still have to multiply this to my remaining zero. So I'm going to erase my board and give myself a little bit more space to complete this. I left off with x squared minus 4x plus 1 times x minus 2. And I'm going to go ahead and distribute using the arrows for this problem, but you could very easily use the box again. Combining like terms yields me a final answer of x cubed minus 6x squared plus 9x minus 2. And again, in this problem, it allowed me to assume a leading coefficient of 1, so I didn't need to find the missing coefficient in this example. Our last algebraic example is using imaginary zeros, and this relies on the conjugate one more time. So for this problem, we're given a zero of x equals 4i, x equals 2, and x equals negative 2, such that f of 0 equals 16. Like last time, I'm going to save the f of 0 until after I've set up my factors. And like the radical problem, for every positive I, there has to be an accompanying negative I. To set these up as factors, I get x minus 4i, x plus 4i, x minus 2, and x plus 2. Again, with multiplication, we're going to want to multiply these pairs together. And when we're finding our front coefficient a, it's best to do it when you only have real factors. So I'm going to stick the a in front, knowing that I need to deal with it later. And I'm going to multiply this portion of my equation together, which gives me x squared plus 4ix minus 4ix minus 16i squared. Since these are a difference of squares as well, it wouldn't hurt to go ahead and multiply these together, knowing that the positive 2x and the negative 2x are going to cancel out. What do I get when I simplify these polynomials? Well, in here, the 4ix's eliminate. X squared negative 16i squared is positive 16. And in here, the 2x's eliminate, and I'm left with x squared minus 4. Now, I have a simple enough equation that I can reasonably solve for the missing a. Here's where I'm going to input f of 0 equals 16. 16 equals a, 0 plus 16, 0 minus 4. That gives me 16 equals 16 times negative 4, negative 64a, and that leaves me with a final result of a equals negative 1/4, although you could also say that a equals negative 0.25. Let's write our final equation fully multiplied out. So I left this version of the equation on my board, that way I can reference it. F of x equals negative 1/4 x squared plus 16, x squared minus 4. My last step is to distribute these together. X to the 4th minus 4x squared plus 16x squared minus 64 is x to the 4th plus 12x squared minus 64, all with a negative 1/4 in front. So my final answer is f of x equals negative 1/4 x to the 4th minus 3x squared plus 16. And this concludes part 1 of the video notes for writing polynomial equations, where we focused on writing the equations algebraically given the zeros.